In the picture, you can see some crops flooded by the tropical storm Julia in 2022. The second aspect that I mentioned before is the use of space technology to identify seasonal variation of water body. Why is important? Because we have some case that the people do agriculture in these areas. And this is that the case is the fluctuating land area in the upper part of Cerro Grande wetland. This is the most, this is the bigger reservoir in the country. If you see this image, you can see the #1 area. This is the Cerro Grande wetland. So these fluctuating land areas correspond to the banks of the reservoir that are exposed during the dry season. But these lands are very important because this area have high productivity value due to the degree of the fertility and the humidity. To map these areas, we processed Sentinel-2 images from 2018 to 2023, and we found the area is more than 3,800 hectares. But I want to mention also an example of the floods occur in this area. In 2022, during the dry season, when the people cultivate, a flood occurred and generate losses in crops. Considering the same study case in the wetland Cerro Grande, our study says that the farmers and the artisanal fishermen in the area are affected by soil and water pollution, and also the proliferation of pests and diseases and hyacinth of water. Regarding to the hyacinth of water, you can see in the pictures the hyacinth of water on 2019 in this wetland. And we obtain the percentage of area covered by hyacinth of water, and the percentage is more than 50% of the total water body. You can see the figure to the right. Okay, in the next slides, I want to show you some applications that my institution, the Ministry of Environment, is working on for different users. The first one is the data cube. This data cube is a platform. It allows integrate several data sources like MODIS, Landsat, Sentinel-2 coverage map generated by Rapid Eye, and LiDAR and historical aerial images. This data cube have many applications, but I want to mention some I want to mention the applications related with the water management. Assessment of the tree cover loss, increase and reduction of water meter bodies, and the water quality assessment. The second applications is the use of the artificial intelligence to communicate with agriculture sector's users. This application is called Chateau. Chateau is a chatbot that allows to consult many information on different hazards like earthquakes, landslide, and the weather, of course. The information available in this chatbot is the precipitation, wind speed, temperature from yesterday, today, tomorrow, and the next week. Also, there are information of climate outlook, impact-based monitoring, forecasting, special reports of the different hazards. Okay, and the outlook and the future things to do. I enumerate 3 things that we need to do in the future. The first one is the implementation of El Salvador Data Queue to support efficient analysis applied to the water management. The second one, disclosure of information to interested parties, population affected, different levels decision makers, sorry. And the last one is incorporate climatological information and show how to interpret enclosed issues. Finally, the conclusion, special technology applies support the estimation of impacts, damage, and losses, especially in crop areas, due to the occurrence of extreme events that influence the country. And integrate analysis with climate and economic data needs to be performed in order to provide responsible estimation of losses. Artificial intelligence applied in chatbots to improve the communication with users grouped in the agricultural sector constitutes a tool that improves the early warning system and maintains that sharing of information to support decision-making process, reduce losses or damage, and guarantee food sustainability. Thank you very much for your attention.
Thank you very much, Anna, for a very nice presentation and being on time. We open the floor for 2 questions online, if you have any, and as well as for our participants here in person. Yes, we have one question there. Please introduce yourself and then the question, please.
Hi, I'm Jorge. Thank you for the presentation and the tools that you showed us. It's an amazing job. So congrats on that. I wanted to ask a little bit on the quantification of losses and damages on crops that you mentioned. If there is something already, like if you can give a couple of details about that, or if that's something that would be enhanced later on. And the other thing is, where is all this processing taking place? Like, is that in a software, in a platform, or where is that being conducted? Thank you.
Okay, thank you for the questions. Regarding to the damage or losses in the field crops, I don't know exactly because my analysis is just this is the area affected. This is the crop affected, but the people need to know how can they do. But in my case, my limitation is just to show the map. And the second one is I started to use the new platform of Copernicus that I don't remember exactly the name, but it's the new platform. Using an API process, and it's easy to use because you can choose the area and the time, and you can download or process the information in few minutes.
Hello. ¿A dónde se puede accesar a chat o
Operation license side of the chat or the website.
Yes, the chat web is in the web page of the ministry. If you, I don't know how to share the link, but if you write in the Google Chrome, you can write MARN, it is the name of my institution, and the chat is the first thing that you can see.
MARN is the Ministry of Environment?
Yes, yes. In the main page, the chat is there.
Okay. Is chat based on ChatGPT or similar?
No, I didn't work with the performing the chateau, but it's another kind of artificial intelligence. It's not ChatGPT, but it's similar. because the information is only for the observatory information, natural hazard reporting, special informs.
Can chat to deliver information to mobile phones,
Yes, of course.
WhatsApp, via WhatsApp or by email, you know?
At this moment, just in the website.
Okay, perfect. Thank you very much.
You're welcome.
Thank you very much. Let's give a round of applause to Anna, please. Now we have our third presentation. Our third presentation is on flood modeling of the Cagayan de Oro watersheds. And this is from the Philippines, and giving this presentation, we have Faye Ociones, and Ms. Faye Ociones is an environmentalist, and she's worked on research for the Philippines government. Her research is primarily on watershed management and vulnerability and risk assessments to inform policy as well as decision-making. So Faye, you have 12 minutes.
Okay, good morning. My study is in flood modeling of 5 watersheds in Cagayan de Oro City using terrain analysis. So in the Philippines, about more than 60% of our land area is located in mountainous regions, no, or the uplands. So usually our big cities are located in big valley plains, which are really very vulnerable to flooding. So the study really aims to determine the cause of flooding in these major cities in the Philippines. So Cagayan de Oro City is one of those major cities that we have. So next slide, please. So Cagayan de Oro, as I have said, is located in a large valley plain. That's the location. No, so I use terrain analysis, and this involved the geomorphological and spatial assessment of the watershed in terms of watershed shape and relief features and channel morphology. Particularly, hydrological parameters used include circulatory ratio for watershed shape, and the bifurcation ratios, stream densities and frequencies, and relief ratios. So that's also the parameter that was used by Dr. Dietrich Schroeder of the University of Applied Sciences in Stuttgart, Germany. So that's the same parameters that he used in analyzing for terrain analysis in the watersheds. Next slide. So these are the 5 watersheds. This is the drainage map of the 5 watersheds. This is the Iponan watershed, Cagayan de Oro, the Bigaan, and the other are Umalag and Liponan watershed. So as you can see, this is the drainage pattern. In watershed, this pattern is called the dendritic pattern of water drainage pattern, no? Dendritic. Actually, dendritic pattern of watersheds indicates that the high erodibility of the soil, no? The dendritic pattern. So we delineated this one from the 10-meter interval topographic map, which is a higher resolution topographic map. So we delineated this one. And for getting the bifurcation ratio, we had to do a stream ordering. So we used the Strahler and Horton method of stream ordering, which if you have two first order streams meeting, so the next order stream would be 2. And if you have 2 stream order meeting, that the next stream order would be 3, and so on and so forth. So the result of the terrain analysis shows that there are 2 watersheds that are highly vulnerable to flooding. This one is the Cagayan de Oro and the Iponan. So I want to concentrate or more detail on these 2 watersheds. Next slide, please. So this is the Iponan watershed. It is a 6th order stream. The land area is about 47.5 plus hectares, considered as a medium-sized watershed. So in terms of usually we analyze for drainage density. Drainage density is the number of streams, no, the number of streams in a given area over its area. And stream frequency is the length of all the streams over the area. So if you have high values for this one, that means that they would have higher peak flows, or they're vulnerable to flash flooding. And bifurcation ratios is the ratio of the number of streams of a given stream order compared to the next stream order, not the number of streams. So again, the lower values would mean that it has it's vulnerable to flash flooding. For circulatory ratios, the ratio is up to 1, which means that it's a perfect circle. Of course, in reality, there is no perfect circular watershed, but circular watersheds, no, let's say it's a 0.8 or 0.7, that is a high value. So it's really prone to flash flooding, because in circular watersheds, water from remote area in the watersheds would arrive at the main channels all at the same time. So it's vulnerable to flash flooding as compared to elongated watershed, where the water have already drained down before the water from the remote sites would arrive in the deposition zones. So in terms of circulatory and bifurcation ratio, Iponan watersheds is highly vulnerable to flooding. No? And we looked into the activity upstream. The picture here, as you can see, sedimentation is high. And this is an upstream river system. No? Because what they do there is they extract the boulders and the stone in the river, crushed it for gravel. So this changes the geomorphology of the river system. And these stones are actually, they serve as a deterrent to the high velocity of water, no? So they changed that. As you can see in the remote, in the imagery on the right side, so in the ocean, in the ocean, you can see the high sedimentation that's occurring downstream because of this activity. So we really recommend, because flooding would be aggravated, no, if you get the stones or the boulders up the river systems, especially in the upstream and the midstream. So we recommended that this activity should be regulated or banned totally. Okay, so next slide. This one is Cagayan de Oro River. So it's 130,000 hectares, considered as a large watershed. So it's the same with Ipono River. Bifurcation and circulatory ratios are also the cause of high flooding in Cagayan de Oro River. Cagayan de Oro River. And the upstream portion comes from really high mountains in the area. We call those mountains Mount Kitanglad and Mount Hinatungan. So they are about 2,000 meters above sea level for Mount Kitanglad and 1,700 meters for Mount Hinatungan. So these have high or steep slopes. No? The Iponan River is the Iponan watershed is also vulnerable to pollution, actually, because dislocates the landfill of Cagayan de Oro River. So, and also they have gold mining upstream. So for mercury and copper, and also what they call this other hard metals, they are high in these watersheds, watershed, Iponan. So, next slide, please. So, we mapped out in the deposition zone, the left side is the Iponan River. So the red areas are the 1 to 5 meters above sea level elevations, and the blue, the 5 to 10. So these are vulnerable, no, to flooding. So we recommended that these areas be buffered. The span of the buffering in the river should be longer, no? Because in the Philippines, we based our river buffering on land use, no? So for urban areas, it's 3 meters, for agricultural, 20 meters, and for forested areas, 40 meters. So we recommended that they should not base buffering of rivers based on land use, but it should be based on the terrain, terrain and its vulnerability to flooding. So for the deposition zones, for critical watersheds to flooding, it should be not only 3 meters. No, it should be from 5 to 10. Okay, so next slide, please. So we also recommended the land classification, the green app is recommended to be forested. This is the 18% and above slopes. For soil and water conservation, they should be forested. And the yellow is the alienable and disposable land classification. But as you can see in the existing land use map that was classified using the ALO's imagery, already there is agricultural and grassland have changed these forested areas. So this is one that have aggravated the flooding that is occurring in those areas. Next slide. So we also recommended that the critical areas in the river systems like the river terrace, the deltas and islets, no, they should not be, the land use should not be for urban or for built-up areas. That should be reversed for protected areas. Because in 2011, our whole barangay, which it was in a river terrace, the population was more than 3,000 during a very strong typhoon that occurred at night. The whole barangay was washed away, so the mortality rate was really very high. So next. So aside from buffering, I've already mentioned that a while ago. So reforestation should be implemented in the river banks and also for steeply sloping areas. Next. So I've already mentioned that. So next. So you should render critical areas as protected areas and no build zones, and to increase buffer zone areas. I've already mentioned that. So regulation when it comes to land use changes, especially in the upland areas. Next. So thank you very much for listening.
Thank you very much, Lei. There's room for one question, real quick question, if there is any. I don't see any. Is there an online question? No, I see no question there. So let's go on and thank Dr. Lei. We go on to the next presentation, and our next presentation is leveraging multi-satellite remote sensing data and machine learning for flood risk assessment in Namnoga River Basin. And this is from Lao PDR. And making this presentation, we have Saktavong Mangeshan. He is at present with the QC Institute of Technology in Japan. Let me just give him a quick introduction of his. He's a university lecturer at the Electronics and Telecommunication Department, Faculty of Engineering, National University of Laos. So in addition, he's also the national point of contact of the Space Generation Advisory Council from Laos. So he's been promoting this space technology in a number of locations, including for education, for schools and universities. So let me now welcome Sak Devong Mangashan for his presentation. If you would kindly please load your presentation and start. You have 12 minutes. Thank you.
Hi, my name is Saktawong Mankasem. I am a PhD candidate at Kyushu Institute of Technology in Japan. My presentation today is leveraging machine learning and open source satellite observation data to assess the flood risk in Namgyum River Basin in Lao PDR. So this is the contents. So we have the overview introduction, we have objective of the research, we have methodology, result and conclusions. So let me give briefly about overviews water resources in Laopedia. If you can see the maps, Laopedia is landlocked in Southeast Asia with the total area about 236,800 square kilometer. So our population now is 7.7 million in 2024. In 90% of the country, territory is located in the Mekong River. So the monthly river flow by the patterns of the rainfall is around 80% in flood season during the rainy season and 20% drought season in the dry season. So Laos is the landlocked country, but we have abundant of water resources, which there are total 62 river basins from the small basin area to the large basin area. So our introduction, we would say that flood is one of the most frequent and damaging natural disasters that have damaging the human life, poverty, infrastructure, environment, and socio-economic losses. So you can see this when the river bank is overstocked, the water overflow to the floodplain, posing a danger to the society and community. So this is a case study in Namgyal River that we have affected from the riverbank overflow. So the frequency and severity of the floods are expected to increase due to the deforestation, human activity, and global climate change. So our research aim and objectives: first, we want to predict the flood substrate model as well as the risk assessments based on open source satellite remote sensing data, GIS, and machine learning, and to analyze its possible effect on the different land use land cover classes population, to find out the aggressive flood susceptibility zone in Namgyal River Basin and classify the whole basin area to the flood classes starting from very low to very high. To evaluate the compared towards other machine learning, so we selected the three machine learning algorithms. So we have artificial neural network, random forest, and support with the machine. Also, our research will be contribution to the national strategy on disaster reduction, especially for the Sendai framework for disaster reduction from 2015 to 2030. And also this research can promote alignments with the objective of sustainable development goals, especially for SDG 11, sustainable city and community, and also SDG 13, climate change. So our study area, if you can see in the geographic, like Namgyal River Basin cover 16,906 square kilometer with the elevation ranging from 2,569 meters above to the sea level. So this have floods happening in 2018. So we can get this from the social media and also from the news. So the river length is approximately about 472 square kilometer, covering to 19 development districts, spanning about 6 provinces, and also represent 2% of the total area of the Mekong River basins. However, the Namgyal River Damgum River Basin had many issues, such as like we have water is used for various purposes. We also have hydropower developments. Irrigation scheme have increasing development throughout the basin. We also lacking of sub-basin management plan and also impacting water-related disaster like flood and droughts. So for our methodology, we use like historical data from Sentinel-1. We also have floods inventory data. We have total like flood location 388 and also non-flood 388. So 0 is 11% in no floods and 1 is 11% in floods. We also have create the condition factor. Total we have 11 condition factor. So we also use the Aulo Pasa Dream, the light parameter for fast condition factor. We also had features suitable tests with speed 70% for training and 30% for testing. So we also use the machine learning model to do comparison, and we also have like model validation using area under the curve of receiver operating characteristic, and also we use we get the reduced land cover effect for to the population and also to the reduced land cover. So this is our results. In our result, we have like we use a feature selection and evaluation using the for example variant efficient factor. We also have tolerance and also we have pressure correlation and also information gain ratio. If you can see this one in the information gain ratio, slope and elevation emerge and high influential with the value 0.49. However, like rainfall, distance to river and curvature aspect being very less information factor. The multicollinearity test showing the slope had the highest variant inflation factor, following by topographic witness index. However, we can see no significant collinearity was observed among the selection condition factor. And patient correlation coefficiency clarify slope and elevation emerge pivotal. So our result for machine learning. So based on RUROC, if you can see in the graphs, random forest demonstrated superior performance over the SVM and NN, and also the random forest and SVM showing the highest accuracy by following by the NN and with the 91% accuracy. Likewise, the random forest and SVM exhibited the highest F1 score also, about 95%. So the mean square error and root mean square error, the random forests are the lowest, exhibited the best performance. So in our result, we would say random forest is outperformed than SVM and NN. So this result for the fast substability, if you can see from very high, we can see the NNs showing the highest percentage for 44%, and the high fastability map, we can see like SVM is a high percentage about 12%, and also moderate, we can see the random forest is showing the highest percentage about 18%, and low subsidy area, we can see both like random forest and SVM had high percentage subsidibility area, and very low, we can see random forest is also high percentage subsidibility area. So in this result, we can show the effect of population and effect on land use land cover. From the analysis, we can observe the number of people vulnerable to the flooding ranging from the 650,000 people to 685,000 people, which is 85 to 90% of the population. So you can see in the right in this figure. And also affects land use land cover change. The high and very high subsidy area are agriculture, paddy, orchards, and built-up area, clearly showing the flood's high probability affecting activity of the people there also. So in this one, we're showing the land use land cover and also the population. So in this, the population area lying downstream of the Namgum River, you can see in this one, is the major settlement are highly vulnerable to flooding, and the upstream of the Namgum River reservoir, for example in Wang Vieng and also Back District, and also vulnerable to flooding.
You have 1 more minute, please. Please kindly wrap up.
So in our conclusion, we want to conclude like Lenovo Forest is outperformed than SVM and NN, achieving the highest accuracy based on the receiving operating characteristic, and also slope and elevation emits a key factor effective fast occurrence, with the low lie area being more susceptible due to the water accumulation, and a possibly 85 to 90% of the people are highly vulnerable to flooding within 260 to 280 square kilometers of the built-up area. Lastly, the study underscored the significance of informed decision-making in disaster reduction, urban planning, community preparedness, emphasizing the important accuracy flood forecasting model, and also advanced warning system guiding by the critical information factor and identifying in this research. So thank you for your attention. So this is my contact detail and my email. You can contact me if you have any doubts and also want any information about Namgam River basins. Thank you so much.
Thank you very much, Mr. Savalan. We do have, time for one question. If there's any question from the audience here or online, please. Well, isn't? All right, so we move on. This was a presentation that was recorded, I understand. So we move on to the next presentation. It was an interesting presentation indeed, talking about the application of machine learning and AI technology, which is coming up quite fast in terms of its applications. There are, of course, many areas where better understanding needs to be made. So let's move on to the next presentation, which is also online. And this presentation is on satellite-based framework for comprehensive assessment of crop loss in flood-affected regions. This is from the Sindh flood 2022 in Pakistan. And making this presentation, we have Professor Sawaid Abbas. Professor Sawaid Abbas, he's working at a Smart Sensing for Climate and Development GIS Center at the University of Punjab, the Center for Geographical Information, University of Punjab. He's a spatial data scientist who works at the nexus of earth science, ecology, and climate change through leveraging remote sensing, machine learning, and strong domain knowledge. His key work involves forest succession, drought, and rangelands, which were accomplished through collaboration with many different institutions, which includes WWF, also ICIMOD and ICRAF, AFCD, and KFBG, all these acronyms I'm sure some of you may be knowing. But let us now welcome Professor Abbas. So Professor Abbas, please kindly have your presentation loaded, and you have a total of 12 minutes. Thank you. Professor Bas, can you hear us?
Hello, hello,
Yes.
thank you very much. So will you play my presentation? I shall play by myself.
You please upload your presentation so you have the control. And then, yes. We do not see your presentation yet, Professor Bas.
Yeah, just let me share screen. Okay. Yeah.
Okay, yes, it's there.
Okay.
Please go ahead. You have 12 minutes.
Okay. So thank you very much, and sorry for this little bit interruption. Okay, my talk is about development of a rapid framework for comprehensive assessment of crop losses in a flood affected region. So there was a severe flood in August 2022 in Pakistan, in Sindh province, which is in the south of Pakistan. And since there was a flood, and we have to look for, as a developing nation and some other part of the world, for loss and damage fund. So for my colleagues with EC Mode, Dr. Faisal, and other friends from other institutions, so we develop a consortium to develop a rapid methodology to understand what are the losses actually, and what we can ask for the aid, and to help us, also to help the affected people, and to cover up the losses. So this was actually to plan to use the satellite technologies to understand how much we have lost and what are the losses to the cropland, especially in this region. So this is the overall objective of our study. We used pre and post-flood images. I think this is a very state-of-the-art framework for such kind of a studies, and I am thankful for our previous presenters. They have a detailed description on how we can use these kind of technologies and the methods for flood mapping. Okay, let me a little bit explain about my study area. So you can see this is about at the end of around Pakistan, in the south of Pakistan, the Sindh province, and it is like one of the biggest provinces, one of the five provinces in Pakistan, and then the one thing we need to note that its mean annual rainfall is about 150 to 180 mm generally, and most of this rainfall happened fall in July and September. But in August 2022, so you can see the total rainfall, like it exceeded at some station. It was recorded only in August, like 1200 mm. You can understand it is almost at some places 10 times higher, and in Balochistan province it was 6 times higher rainfall as recorded previously, and then in the Sindh province it was 7 times higher the rainfall with respect to historical averages. So it was a lot of rainfall, like heavy rain shower. So we look up into the about the rainfall dynamics, and then to understand, okay, from the station data, we may not have a complete picture of overall spatial distribution of the rainfall. And then we use a GPM, Global Precipitation Measurement Mission, to understand the spatial pattern of the rainfall. So here you can see the dark blue patches in the south part of Pakistan, southeastern part, which indicates that the heavy rainfall, which are around more than 800 mm to around 1000 mm. So this was a region which was mostly affected by these rainfalls. Okay, so the rainfall is one phenomenon, and then the another part is waterlogged or the water inundation areas. So for this, we use the Sentinel-1 images, which are synthetic aperture radar. Our previous presenter also explained it very beautifully how they can use this technology. So we just use those pre and post flood images to map the extent of the flood. So this was our second task. And then we realized like around 1/5 of the total study area was waterlogged. Uh, in this, we can see that like in this region, the northwest of Sindh province are northeast of the Balochistan province. They were waterlogged area over here. And then the situation was further unfortunately exacerbated by the heavy discharge from the barrage very next to it, the Sakhar Gudu barrage. And then there was hill torrents from the neighboring hills in this region, Kirthar mountain range, and then it caused a lot of flooding over this region, like in this part of the study area. Okay, then just to emphasize what has happened there was numerous news stories, and then like you can see CNN how they reported it like 100-kilometer wide inland lake. So this flooding has caused like from satellite images, so you can see this on the middle image, the 31st August, it formed like an inland lake. So that was, and then waterlogged for a very long period of time. So these are some another insights where we can see the red, the blue area is indicating the flooding. Okay, the flooded, then we, based on those flood water extent map, we calculated as our aim was for response action, then to help those affected communities and to raise some awareness. So we calculated at district level how much district, like you can see that most of the district, like more than 50% of their districts are completely underwater. Okay, then the next step was to calculate the impact on the cropland, and for this we use the LDVI image. This was also from the satellite remote sensing. Primarily, it is an NDVI, normalized difference vegetation index, which indicate about the vegetation health. So we took the difference of pre and post flood images, and then we can plot. You can see in the image C in the top right corner, which indicate the difference. Here the red areas are indicating where we have a significant crop losses. Technically, it is vegetation losses, but we know that there is mostly these are crop area losses. There are mostly crops in this area, so we can say that this is like the change in the greenness value of the crops. Okay, so then you can see this in the top left corner. There is a big one red patch, and one red patch is over here. I will explain it in the coming slide. Okay, so then to understand which crops has been affected and in this region. So we had a rice production like map, and then the three major crop: rice, sugarcane, and cotton. So we can see that in this part of in the first image, top left corner, we can see this is mostly rice crop over this region, and then in the middle is the cotton and the sugarcane crop. So which means that mostly affected was the rice crop because the overlay. Then based on this, you can see that the seal wise, this is another sub-district level region. We also calculate the crop area, and then how much is the damage to cropland in those sub-district level, and then we evaluate the percentage losses to cropland in those areas. So we evaluate like rice, cotton, and sugarcane. They lost around 80%, and then 61% of their overall loss in the crop. And then which actually cost us around 1.3 billion US dollars. Apart from these three major crops, this region is also known for other vegetable crops like tomatoes, onion, and chili, and they also contributed to around 374 million US dollars. And I know at that time when there was a flood, so we had like spike in the prices of tomatoes and these onions. So if in a overall scenario, if we I conclude, I think this was made by the CMOD's team. This very good illustration that summarizes of our whole study. Total national average of the like 243% higher annual rainfall in August 2022. And then in Balochistan, we have around 600% more rainfall, and then in Sindh around 700% rainfall. And around 14.5 million affected people in the Sindh province. And this whole overall in 33 million people were affected across Pakistan. And then when we calculated the losses to crops, and we then converted into like evaluate how much has been lost, like 4.9 million hectares of cropland area were lost, were like somewhat affected. The total area of cropland was around 5 million hectares, and out of which more than 50%, like 2.8 million hectares of the cropland were affected. And then if we evaluate the production losses for the rice, it was 1.9 million tons, and then which cost around 453 million US dollars. And similarly, sugarcane for 485 million, cotton 485 million, and then sugarcane around 273 million US dollars. Apart from that, we have other losses for livestock losses of 313 million US dollars. So overall, like we try to integrate space technology and then the impact of flood to convert those losses and to estimate actually into loss and damage, to build some statements over loss and damage due to these flooding in that Sindh province. And we are really looking forward to transform this exercise, actually a framework, into a more dynamic system, which can automatically evaluate when such event can happen. Okay, so we have already published this work. I know this is a very short talk. One report is published by ECMOD, and then we also published this work as a research article in scientific reports. So I think I should actually make a QR code for this for the audience if they can scan it. I'm sorry for that. Thank you very much for listening very patiently.
Thank you very much, Mr. Abbas, for this very nice and concise presentation. I think you've covered quite a lot with the framework as well as the examples of collaboration across institutions in coming up with very timely products, particularly crop estimation. I recall Dr. Faisal, actually, he's a colleague of mine that you referred to, that you worked with. So we can take one question if there is any from the audience here or online. Is there any question that we have? Any burning question? I don't see any. So thank you again, Dr. Abbas, and a round of applause for him, please, again.
Thank you very much.
Yeah, so now we proceed. Yes, Nina? Nina has one question. Actually, I was conscious of time and going quite quickly, but let me give Nina the floor here for one question.
I'm sorry for the interruption, but I would be curious to learn how easily can we apply this framework, as I would call it now, to other regions in the world? And is there any training material available on how others can use this? Because I think we have increasingly many areas being affected from such floods, and given the food security questions that also arise, this could be very useful.
Thank you very much, Inna, for a very actually interesting question. I think that's why we have published a scientific paper also, which is explaining the methodology, which is very straightforward. May not be for a layman, but for a little bit of knowledge of remote sensing analyst or GIS analyst, I think they can easily implement it. There is almost all these data sets which we have used, they are open source and they are available, except from the local knowledge about the economic cost or the what kind of a crop area is there. So if we can, we just need that from the local knowledge. Otherwise, all that processes are there automated, and they are actually well-established methods, which we can easily applied. In this study, we also use the Google Earth Engine. You know, it is an open source cloud platform, and we don't need to download the data, and we don't need to do any rigorous processing. We can just run some codes, and it can give us our desired search. So I think the paper and the report, they have very good in detail methodology how we can do it. And it is a very simple and straightforward. And it can be applied, I think, almost everywhere in the world, except we have the, if we have those kind of a data set about the crop production, crop type data, because the global data does not have the different crop types.
Yeah. So thank you very much, Dr. Abbas. I think just to add on to that, in the AC mode, my organization provides these trainings through the Surveyor program also. We have the Surveyor
Yes.
HKH, and on a regular basis, we do have trainings on Google Earth Engine, application of
Yes.
space technology for crop monitoring, crop loss estimation. So these are provided on a regular basis, particularly for the people in the region, but this could be, of course, shared with wider for other regions too, for their benefit. I will definitely convey this to my colleagues back at home. All right, thank you very much again. Round of applause for you. You get a second
Thank you.
round of applause.
Thank you very much, Sandra,
So
for
now,
adding up.
thank you so much. Yes. So let me now go to our last presentation for this particular session. We have this presentation on analysis of drought and flood abrupt alteration events and their agriculture impacts in Kenya. So this is not only floods, but we're also talking about droughts. So you must be curious, what's this drought, floods, alteration, abrupt alteration. So making this presentation, we have Betty McKenna. And Betty McKenna, she is a graduate student at the University of Nebraska, Lincoln. And she's, pursuing her master's. So over to you, Betty, for your presentation. I'm sure everybody's eager to hear what you have to say.
Good afternoon, everyone. Thank you so much for this opportunity. So my name is Betty, and I will be presenting my research. I'm doing my master's program, so I'll presenting part of my research, which is analysis of drought, flood, abrupt alternation events, and their impacts in Kenya. So I'm looking at a number of impacts, but for this conference, I'm just going to touch on agricultural impact. Okay, so Kenya is one of the countries in Africa. It's in the eastern part of Africa. So it experiences two seasons, wet and dry season, and the rainfall pattern is bimodal. So we have the long rains during the March, April, May season, and the short rains during the October, November season. The interesting thing about it is that 80% of the Kenyan land is arid and semi-arid. So basically a lot of drought during the dry season. So drought is a big challenge for Kenya, not just in Kenya, but for most part of East Africa. So hypothetically, during the dry season, as I said, it's usually dry. But then during the wet season, there is the land is green again. The water sources are there. So during the dry season, communities go through a lot of challenges because most of the land is arid and semi-arid. We have a lot of pastoralism. So they move from one place to another in search for pastures, long distance to water resources, especially during dry season. And they always look for wet season so that they can do agriculture. They can have enough water for their cattle, for home use and all that. But then the problem is during the wet season, there is that abrupt shift from dry season to the wet season. So the rainfall is now usually So the rain, other than the rain being a blessing, it's more of a disaster. So I'll make a reference to one of the events that really what that motivated me to do this research was in 2020. I was in Kenya then. So there was, after a long dry period in 2019, there was all of a sudden a very intense rainfall for one day that killed 20,000 livestock in one day. So this motivated my research, and that's why I'm looking at the impact of abrupt shift from drought season to flood season. So from previous research, compound events have been really becoming a big disaster, not just in Kenya, but globally. So here, I did a research, and from the results, it showed like 11% of drought events have been followed by at least one flood event globally. And also, Zhang from China did an analysis of impact of abrupt shift for tobacco. So my research question will be investigating historical trends of abrupt shift in Kenya, and also looking at the agricultural impacts of this shift. So I'll go to my methodology. So I used CHAPS data, precipitation data, which is gridded data set, 5-kilometer resolution. I looked at three periods. I said Kenya has bimodal rainfall patterns. So from the dry season to the short rains, which is from August to November. So August to September as my drought months, and October to November as the start of the short rains in Kenya. I also looked at November to February. So that's the ending of the short rains to the dry season. And my third season, which is really important, was from the dry season to the start of the long rains, which happens in March, April, May season. So I standardized the data, and then I used an index called Long Cycle Drought Flood Abrupt Alternation Index. And then I incorporated the impact data from the FAO. So I used the crop yield and the animal produce from the FAO yield database. So I'll jump to the results. My first map was showing the abrupt shift from dry season to the start of the short rains. That is from August to November. So from the map, there were two events. So the first one I classified as drought to drought, where the drought in the dry season extends to the wet season, and that is it's visualized in the red shades of color, where the yellow shows there was a little moderate shift, and the red shows there was an intense abrupt shift from drought to extreme drought. So the second one was shift from drought to floods. So that is visualized in the shades of blue, where the lighter shades shows there was moderate, and then the dark shades shows there was intense abrupt shift to floods, and then the gray color shows there was no abrupt shift. So you can see major drought to drought events, mostly in 1983, 1988, 2007, 2013, and mostly from 2018 to 2022, we have had smaller abrupt shift from drought to drought. And then from drought to floods, I will go reference to there was 1997, 2011, 2015, 2019, and 2023. So the spatial patterns of these, most of them are in the northwestern Kenya, Western Kenya, and the northeastern Kenya. So the next map shows the abrupt shift from the dry season to the start of the long rains. The long rains is it's a very important season in Kenya, because most of the farming happens during this season. So then major drought to drought events, 1993, 1998, and then a number of abrupt shift to floods. From 2013, you can see a series of blue colors from 2013, 2018, 2020, 2023. One thing you realize is that there is high magnitude of abrupt shift during this season, both from drought to drought and drought to floods. Okay, I correlated my analysis with impact data. So one thing I realized, there was a low negative correlation. I correlated with the drought to floods event. So there was a negative correlation showing like increased precipitation has negative impact on maize and camel meat production. So as you can see, the correlation there was low. One challenge is analysis of impact data, because I was analyzing at country level, and I was taking one value for the impact. Maybe that's why the low correlation is there, but still you can see it's a negative correlation showing like precipitation is good, but a lot of it has a lot of impact in agriculture. So I'll jump to the conclusion. So there were three major patterns of drought to flood events. So most of them were cumulative across the season. So they started accumulating from OND season to MAM season, and that has a lot of impact to the communities. So one thing I realized is drought to drought events have reduced in magnitude, but increased in frequency. But then the drought to flood events, abrupt shift from drought to flood event have increased in frequency. So just looking at the map since 2012 to 2013, that is like 11 years. Out of 11 years, we've had 8 drought to flood events. So you can see almost every year we have a drought to flood event. So and then we see a negative correlation of impact data with agriculture and livestock. So I sort of updated the slides. So I also had some additional point on adaptive strategies that we can consider for this one. And one of them was the soil management. So I feel like soil erosion, conserving the soil could alleviate this abrupt shift event, because then we can conserve a lot of water that just goes to waste and causes floods, for groundwater recharge, and also for agriculture, because a lot of precipitation is not useful to the communities, but how can we conserve it for drought season? And then incorporation of this abrupt shift into our early warning system. As you can see, the climate is changing. So even our early warning system should be able to change to incorporate compound events, just to prepare communities and to increase our adaptive strategies to natural event as a result of climate impact. Thank you. Oh, so before I proceed, I want to acknowledge my committee members and funding opportunities. Professor Segai, Mark, and Michael, and funding from Fulbright, University of Nebraska, AGU, and of course UNOSA for giving me this opportunity to present here. And of course Kenya Red Cross, because I was working for Kenya Red Cross before I started my master's program. Thank you.
Thank you very much, Betty, for a comprehensive presentation on your research. Are there any questions for Betty at the moment? I see no hands. I think everybody is getting hungry, a sign towards that. But I have one question. It was interesting to hear, particularly I think we've been hearing quite a bit on floods in general, but what Betty has raised is more the compounding kind of hazards. So it's not only floods, but there is droughts followed by floods, or droughts followed by other different types of disasters. So when you say that it is a way to also prepare the communities well in advance, what aspects of your study looks into preparing the communities? I mean, is it, you said integrating it into early warning systems, but can you elaborate a little bit more?
So yeah, that's a very important, that's a good question. Thank you for the question. So currently I haven't gotten into the integrating into the early warning system, but there is something I want to take up because I do a PhD, just modeling this and incorporating it in the community early warning system. I think that is that would be a good plus for this research. Otherwise, if it just goes like that, it won't have like that impact to the communities. Yeah.
Well, thank you very much. Again, Betty, a round of applause for Betty, thanking her for her presentation. Okay, so thank you again to all the presenters online as well as in person. I don't want to take much time in terms of really summarizing what we just heard, but I had several points here that I wanted to just remind us at the end of the a very interesting session that we've had. So some of the keywords that we had basically that came out from the conclusions as well as from some of the recommendations that were being brought forth. First and foremost, I think it's important to realize that floods is the most severe hazard. I mean, that's no doubt. When you look at different types of hazards globally in terms of impacting millions, so it's the deadliest hazard in the world. I think we heard this from the not only for the first presenter, but also many other presentations that followed. The other point, yes, but it's not only floods, like we heard from the last presentation. There are compounding effect events. So there are disasters that are becoming major challenges to really work with as well as manage. So it's floods, droughts, landslides, particularly in mountainous terrains. These are different hazards that occur simultaneously. And so you need to be better prepared for multi-hazard early warning systems or multi-hazard kind of ways to respond to that. Now, the other third point that we heard today was also many examples of various tools as well as technologies that came forth that are being used for flood risk reduction, flood management, and in general, water resources management. So examples of, for instance, what we heard from WMO was the FFM program on flash flood guidance system and how it's being used. In fact, Costa Rica is one of the leaders in terms of implementing the flash flood guidance system, which I understand and as well as know, as well as we do have in the Hindu Kush Himalayan region where I come from, a flash flood guidance system in the region, both in Southern Asia, that is being organized or that is being implemented by IMD, as well as for the Western region by the Pakistan Meteorological Department. So the other point was that there's a lot of opportunity for AI and machine learning. And particular examples were given in terms of also looking at ways to link it with impact-based forecasting. I think that is something that is evolving and I think needs a lot of attention, because many a times we look at not only what the weather will be, but what the weather will do. So that's where impacts are becoming more important than just saying what is going to happen in terms of the amount of rainfall discharge or the volume of water that is anticipated. Yes, Earth observations fills the existing data gaps. There was examples of for precipitation, for example, the global precipitation measurement data that was used for understanding the spatial extent of the rainfall, as well as the various images from Sentinel data. One of the points that came out strong also was the need for capacity building. So it's not only one-time capacity building, but what we heard was a long-lasting capacity building is essential. So what do we mean by long-lasting capacity building? To me, it is more looking at the institutional capacity building. It should be not at like one of a time, but rather a continuous process of capacity building that needs to be done. That includes training, and that includes various types of capacity building, actually, not only just trainings. Then the question that was asked and also raised was the importance of looking at outscaling and upscaling some of the methodologies and tools that we've heard and examples of today. So how can we learn from the lessons that have been learned in other regions, like, for example, the crop damage estimation presentation that was made from Pakistan? Then definitely, the geospatial tools and technologies, GIS, plays a key role in understanding the risks and vulnerabilities, mapping that, examples that came from Philippines as well as others, which we can use for different types of assessments, and then taking it beyond assessments for more informed decision making. Then I guess the last part was the last presentation really looked at some of the compounding events and how we can integrate it with early warning systems. And that's something that I'm glad, Betty is looking into. And I'm sure there are many other researchers that are looking at these compounding effects and looking at multi-hazard early warning systems. And if you look at the last the seventh target of the Sendai Framework for Disaster Risk Reduction, it talks about the multi-hazard early warning systems, making it available to everybody. And I think that WMO, they have this target of having the multi-hazard early warning system available by 2027 to all. Yeah, so that's all what we also can strive for, using our space-based tools and technologies to contribute to those big targets. So with that, I thank you all for being here, listening. To those that are online also, thank you very much. And I hope you've had a productive session. So over to you, Nina. Thank you.
Thank you to all the speakers for the